All right, let's talk about views. So, oftentimes we don't. Uh, uh, um, well, most times, right? We organize our data, right, in such a way to meet certain criteria, certain standards of avoiding redundancy. Right? We look to normalize our data. We split it off into multiple tables, right? Again, trying to avoid redundancy and the risk of inconsistency. But oftentimes, we want to consume the data in a different way than what it's stored. Right? For instance, as we might go off and split the grades on one table, the students in another table, the enrollments in another table, right? And but then depending on who the audience is, they might prefer to see the data all aggregated, right, into a single view, and perhaps grabbing some values from some table and some other values against another table, right, and see it all as if it were one single entity, right, one single set of records. Even though that's the way we want to consume it, it might not be the best way to store it. Okay, so many databases allow you to create these views, right, that are essentially queries, select statements that are virtual, but allows you to treat them as if they were tables, right? They behave almost the same way as a table. You can create views using the create view statement and giving it a name, and then providing the query, right, that is used to generate this view. Right? That means that now it's going to appear, as if it were a table. You can click on it and you can see the fields and you can see the values. It will look just like any other table, right? But it's not a real table. Right? It's really a query that is perhaps retrieving data and aggregating data from multiple tables, putting it all into one single place, right? Just for convenience, just because we want to consume the data in a particular way. Okay, and unlike other tables where to be modified you need to insert, you need to update, you need to delete. That's the way you modify the table. Views, since they are not real tables, right? They always extract their data. They have always the data up to date if any of the other tables is modified, right? So if other tables modify, if this view depends on those tables, the view will always show the very latest. Make sense? Okay. So here we have an example of creating a view that called current product list, right? That is extracting values from two tables, product ID. From the products table, where discontinued is false, right? So this is definitely extracting only those products whose discontinued is false. So it's a brand new set of products. So notice that I can use it in the select statement, right, as if it were just any other table. Here we've gone and showed you that we can even put spaces in our views. Right? Again, these are not real tables. It's only for convenience purposes. And earlier, our examples earlier where we were using Q1, Q2, Q84, those, right? Those are basically could be implemented as views, right? The view Q60 something, right? And then you can then use it as a query, right, in the next query as a view, right? So here we're showing that the select statement that you can use to create your view can be as sophisticated and as general as you want, right? It could be any select statement, right? So here's products above average price, right? Where we're using two select statements, one inside the other, right? The inner one is grouping, right? Is grouping the entire table and calculating an aggregate function of the average unit price, right? So that calculates an entire unit price, right? Average unit price, and then this is being used in an outer select statement that compares the average unit price to unit price, right? Compares them all against the average one, and then returns only those elements only those products, right, whose price is greater than the average one. And we name it. This is such a convenient query. We use it so often that we can create a view and then use it as any table. And then we could use that in other queries, right? We can do additional queries. Right? So here's another one. We are creating category sales for 1997, right? And where we are presumably extracting from another view, so a view inside of another view, right? So these you could create all these, hierarchies of views. I don't know. Did we have a product sales for 1997? I don't think I have it. So presumably, right, this the product sales for 1997 queries the product table, right, and where the sales year presumably is 1997, right? So that's a view, which is then being used here to group it by category of 1997, and then create a view with all the sums of the product sales for that particular year. Okay, and then it's being used by another select statement that extracts only those records, only those products whose category name is beverages. So it's very, very powerful. Yeah, so all along, right, our Q65, right, that we've been using in other examples, right, they could have been implemented using views, right? So this Q65 equals select can be actually implemented as a view, create view Q65 as select as name and whatnot, right? So it defines it without actually executing it. It executes every time you refer to it, right? Every time you refer to it, it runs again. So it's kind of expensive, right? If you're using views often, right, they can be very, very, very expensive, right? So we need a mechanism that would allow us to have the benefits of views, right? But perhaps, right, mitigate some of the negative of being very expensive, right? That every time, ideally, we would like to cache them, right? Cache them so that at least if no tables that the view depends on, if they haven't changed from the last time, why even rebuild it, right? Why requery it? We could perhaps create a cached version of a view up until at least any of the dependent tables change. Okay. So we're using queues, queries. We can create a view here. The students of 2004. So there it is. We are using Q65, which is what? All right. So this was just selecting the name and the graduation year from students, and so we named it Q65, and then we're using here to filter and retrieve only those students from 2004. And notice that it's like as if we were just embedded, right, and expanded it. They behave just like subqueries, right? They're expanded and reconstituted and re-executed every time they are referred. So they're very expensive, right? Just like any other subquery. So external schema. So the capability of a database providing these external views, right? They're referred to as a external schemas, right? These are not real schemas. These are not real tables, right? They're just a convenience way of consuming the data. So some folks might want to consume the student information and aggregate, their year of graduation, their departments, where they're currently enrolled, what grades they're in, which they're spread over 3 or 4 or 5 tables, but it's very inconvenient. We would want perhaps to create a pseudo table, right, that would aggregate their student IDs, the student name, their GPA, number of courses that have passed, number of courses that have failed, right, to generate a report, right? This we have to generate these reports every quarter, right, to see where we are, and just going to fetch all this data by joining all these tables is just very inconvenient. So we could create a view for this. Same thing, we could create a student course that shows a year offered, the title, the professor, the grade, right, and report data that would otherwise be spread across multiple tables. So to do this, we can create a view for the student courses that goes off and merges or joins 3 different tables and extracts, grades from the enrollment, the professor from the section, the course title from the course table. It goes off and retrieves all this information and puts it conveniently in a single view so that it's easier to consume, right? Notice that we would never actually go off and create a schema like this, right? It doesn't mean that because it's convenient to consume it one way, it doesn't mean that we create the schema that way, right? There's 2 different things, right? One is we want to balance the fact that we want to create the appropriate schema without redundancy, without inconsistency, without bad relationships, right? But at the same time, we can go back and create these convenient views. Now, updating views. So updating views is notice that views are not real tables, right? They are extracting values, right, and rows and columns and whatnot from other tables, right? So updating a view would mean that ultimately we would have to update the table that the view depends on, right? So if we want to update a value on some view on a table that doesn't really exist, we need to identify how modifying a view modifies the original tables that the view depends on, right? Because you're really not updating any real table because views are not real tables. So updating is if we can uniquely identify that a field in a view uniquely maps to a record, right, in the original table, then the update is trivial, right? But if a record or a field on that record is an aggregate, right, of multiple records, right, then the update is not trivial, right? Because a value that you might be looking at a single record, right, might be dependent on 3 or 4 or 5 other records, right, across multiple tables, right? So the update would not be trivial, right? So single tables. So if it's a single table, then it's trivial, right? You know that you're just extracting values from an original table. If they're not grouped, then it's okay, it's easy. But if they're grouped, there's no way that you say, okay, well, the average of a student quizzes is 85. Well, that means that you grouped several records to come to the conclusion that the average is 85. You can't just say, well, no, I want to update the average to be 90. What does that mean? Right? Perhaps you took 10 quizzes. Do I need to update all 10 quizzes to bring up the average to a 90? Makes no sense, right? So we can't go back and update the original records if they have been grouped. If it hasn't been grouped, then yes, right? We can go. If the view is made up of multiple tables, right? Then it cannot be updatable unless it can be uniquely identified. So here's an example where we have a view that we have extracted. The student name, the department, and joining the two, joining the student and department where the majors match. So here's a view that conveniently brings together data from the student table and the department table where they match. Joe in art, Sue in math, and Alice in computer science. So what would it mean? What would it mean if you try to delete Sue math? Right? You're trying to remove that. What does it mean? Does it mean that you want to remove the record from where you extracted Sue? Is that what you're saying? Are you trying to remove the department, right, from where Sue is in the department table? Is that what you want? Or do you want to remove both records from both places? What does it mean? What would a delete there mean? And also, it might be that the database might interpret it in such a way that it's not actually the way we want to introduce it, right? It might, in some cases, if you have an aggregation of orders and products, what does it mean that if you remove the order, does it mean that you also remove the products by which that order is associated, right? So if it's ambiguous, then we would like to be able to specify exactly what we want to do. What about insert? Right, being able to inserting Joe and drama, right? If Joe is already in art, right, but now we're inserting Joe into drama, what does that mean? Does it mean that Joe is no longer in art, right? And we should remove the record for the art, right? If you can only be in one department at a time, right, then it would be ambiguous. You cannot have more than one major, right? Because if Joe would have a foreign key to the art department, what does it mean? That now that foreign key is pointing to the drama department, right? It's no longer pointing. So again, it might be ambiguous. Store procedures in a different slot deck. All right, so let's leave this here.